Dan Goldin was head of NASA with all its preoccupations, but watch his jaw drop. He'd just caught a total eclipse. Whether you're boss of the biggest space agency on Earth or a humble observer, a total eclipse of the sun is the greatest spectacular in the solar system. The diamond ring, an almost magical moment. Within seconds, the moon will completely obscure the sun, an astonishing celestial coincidence. Totality, and it happens because the moon is 400 times smaller than the sun, while the moon is also 400 times closer than the sun. Another diamond ring, and the sun returns. This is not animation, but time-lapse of an actual eclipse. Totality lasted only a few minutes. The whole event, with the partial phase before totality and this one after, took 3 hours. Only when the moon aligns directly between us and the sun is there a total eclipse. We'd have more eclipses were it not for the moon's tilted orbit. It's angled by 5 degrees to the plane of both Earth and the sun, the so-called ecliptic, here in green. During each orbit of Earth, the moon twice intersects the ecliptic. Right here and here. But only on the sunny side of Earth, at this intersection, can a solar eclipse occur. Imagine you, the viewer, are the sun. The moon approaches alignment. A total eclipse. It happens about 70 times a century, although partials occur more often. There's a more common eclipse, a lunar eclipse, where the moon turns red. The culprit is Earth, as it directly aligns between moon and sun. Such a blush can last an hour and 3/4, and logically, the moon should darken. But as it moves into Earth's shadow, our atmosphere bends and filters sunlight to project a ruddy blush. The eclipse is visible all over the dark side of Earth. Back with solar eclipses, sometimes the moon doesn't quite cover the sun. That's an annular eclipse. The cause is the moon's slightly elliptical orbit. For when the moon's farthest away, the full shadow just misses Earth. At a total eclipse, a narrow band of darkness sweeps across Earth at supersonic speed. Only from within the band is the eclipse total. The moon is close enough for a full shadow to touch Earth. That shadow, at the center, is called the umbra. The much wider partial shadow, the penumbra. The day of a total eclipse. TV people are preparing. Cameras have drives to keep the sun center frame as our planet rotates. Filters for telescopes, cameras, and naked eye are vital. Safety-approved glasses are the order of the day. First contact. This partial phase can be as long as 90 minutes. Projected through binoculars, twin images of the diminishing solar disk. Cloud is the fear. This man tries a tinted filter. Dappling through trees, leaves create multiple images of the crescent sun. Totality approaches. The sun is a sliver. Then Baily's beads, as the last sunlight shines through lunar valleys. Totality, and despite thin blowing cloud, breathtaking. The corona, the outer atmosphere of the sun, is normally invisible. Now it can be viewed by naked eye. All around, it's like twilight. At totality, light levels have dropped 1,000,000-fold. Equipment is anxiously tweaked, but the greatest thrill is watching. The planet Venus has appeared. The corona, dancing in the sun's magnetic field, is ever-changing. A prominence has detached as it shoots into space. Rough photography, but magnificent. The crimson plume is hydrogen gas rising 30,000 kilometers. Still in close-up, the return of Baily's beads and the diamond ring. Nobody's much interested in post-totality, especially if it's cloudy. Here's the effect of a total eclipse in time-lapse. Light dips slowly at first, but as the full shadow approaches, darkness rapidly descends. Birds roost, flowers close, and like heralds, dogs bark. Totality can last up to 7.5 minutes. It's an experience no one forgets. A total eclipse arouses deep feelings, and when the sun reappears, primitive relief. Nature has another light show, the aurora, swirling in the upper atmosphere, a kaleidoscope of color. Such displays occur mainly in the high latitudes of both hemispheres. The cause is 150 million kilometers away, the sun. Along with light, heat and energy, and other radiation, the sun emits a solar wind. Whirled outwards by the magnetic field, the wind blows at up to 400 kilometers a second, a continuous flow of tenuous gas and electrically charged particles. These particles are obstructed when they reach Earth. They must flow around our magnetic field. But some connect and are trapped. They spiral down force lines towards the polar regions. The result is auroral displays. Around magnetic north, the aurora is a glowing oval. Energized solar particles are interacting with atoms and molecules in the upper atmosphere. And when there's an aurora in the north, there's a mirror image in the south. This is an average aurora, the light of countless collisions between solar and atmospheric particles. But every so often, the sun throws a tantrum. It's called a coronal mass ejection. Here are several over a week. The solar wind can accelerate to 1,000 kilometers a second. Flares are the cause, monumental eruptions on the solar surface. Now at hurricane force, the solar wind takes just 40 hours to reach us. The shockwave squeezes our magnetic field, the magnetosphere. The magnetosphere is buffeted like a windsock. We get geomagnetic storms and wonderful aurorae. In the northern hemisphere, the auroral oval is intensified and disturbed. It expands through the USA. The aurora induces electrical currents near the ground, troubling the Alaska oil pipeline. Power supplies are knocked out, and satellites sent into a spin. But the great blessing of storms from the sun are the jaw-dropping aurorae on Earth. Colors are delicate. Greens and reds are caused by excited atoms of oxygen, purples and deep reds by nitrogen. The excitation happens at heights of between 100 and 400 kilometers. In the northern hemisphere, the displays are the aurora borealis. In the south, the aurora australis. Celestial fantasia. Astronomy is an ancient science. We've always tried to make sense of the heavens. We built observatories to mark the movements of the stars, the planets, the moon, and the sun. We learnt the passage of the night sky. We saw how it changed, just a little, night by night, a lot, season by season. Different places have different views of the sky, and the same place has different views each season. The ancients put order into the heavens. They grouped the stars into constellations, creating a legend for each pattern. Altogether, there are 88. Here looking north, the autumn constellations from the Northern Hemisphere. And still in the Northern Hemisphere, the view south in summer. And now in autumn. The Greeks named over half the constellations. But not here, for they couldn't see this far south. From the Southern Hemisphere, where the names are more recent, we're looking south in autumn. Of all the constellations, the most glorious, luckily, is visible from everywhere on Earth: Orion. Its pattern links brilliant points of light, really distinctive for the white stars in Orion's belt. But this is our earthly perspective. Fly 2 circles through space and the stars of Orion shift position. It's because they lie at varying distances from Earth. Only when we return to Earth do they resume their 2-dimensional pattern, Orion. In Greek mythology, Orion was a hunter, but he was killed by a scorpion that stung his heel. So in deference, only as Orion sets do the stars of his slayer rise, well away in Scorpius. The band of pale blue is our galaxy, the Milky Way, backdrop to Antares, the brightest star of Scorpius. Scorpius is rich in beautiful objects, and the pattern really looks like a scorpion, especially the tail. This is less convincing. Hercules the strong. And how about Leo, the lion slain by Hercules? In the pattern of Taurus, the shape of a bull? Easier is Cygnus, constellation of the swan. But this could be anything. In fact, Gemini the twins. And who would guess Capricornus the sea goat? Or Sagittarius, half beast, half man? In the northern sky, from the Northern Hemisphere, a popular pattern takes shape. The stars of the Big Dipper, part of Ursa Major, the constellation of the Great Bear. The Big Dipper, known also as the Plough, has 7 main stars. They change position if you go back or forward 100,000 years. It's because the upper and lower stars travel separately from the other 5. The 5 move as a cluster. 2 stars in the bowl of the Plough, or Big Dipper, are called the pointers. Merak and Dubhe show the way to Polaris, the pole star. Polaris is in Ursa Minor, constellation of the Little Bear. The Big Bear was a nymph, transformed for an illicit love affair. The Little Bear, her son, transformed for mistakenly hunting her. In punishment, the god Jupiter swung the pair into the sky and stretched their tails. The spin of planet Earth causes the nightly motion of the stars, and where we are on Earth governs which stars we see. Nights get longer and shorter because Earth tilts in its annual orbit of the Sun, the reason for seasons. Over 4 seasons, as Earth orbits the Sun, our view of the stars changes. Imagine a line extending through the Sun to the background stars. This is how they'd change through a season. We don't see them because the Sun is so bright. But if we could, this is how the Sun would appear to move through a season against the stars. It's the same for the opposite side of the sky, at night. November from the Northern Hemisphere, looking south. From the same place in February. In May. In August. And again in November. But there's one star that barely moves. It lies above the North Pole, Polaris, the pole star. As we've seen, Ursa Major contains the Big Dipper, and 2 stars in the Dipper point to Polaris. While the rest of the sky appears to move, Polaris hardly shifts, whatever the season. An illusion caused by Earth's rotation. It's the same with the south celestial pole, only here there's no marker star. Halfway between Crux, the Southern Cross, and Achernar lies the pole. Around it, through the seasons, the southern constellations appear to rotate, because it's Earth that's moving, not the stars. In whichever season, our position on Earth dictates our view of the sky. From that position, we see only half the sky. The rest is beyond the horizon. In the mid-latitudes of the northern hemisphere, for instance, we cannot see the Southern Cross. But we do see the North Celestial Pole and Polaris. The farther south we go, however, the lower in the sky is Polaris. From the tropics, it nears the horizon. In the southern hemisphere, the red dot is the South Celestial Pole. The farther south we travel, the higher is the pole. From southern Argentina, 50 degrees south, this is the view. Earth's axis points to the celestial poles, but because the planet wobbles, today's poles won't be tomorrow's. The main cause is the moon's pull on our equator. The effect, called precession, is a cycle. Once the star Thuban marked the north celestial pole. Today it's Polaris. In 4,000 years' time, it'll be Alderamin. The cycle takes 26,000 years. With the pointers Merak and Dubhe signposting Polaris, we found the pole star and Ursa Minor, its constellation. Now, from the pointers, a gentle curve through Polaris leads to Cassiopeia, constellation of the Queen. The Big Dipper has another signpost. From these stars, an imaginary line extends to Capella, brightest star in Auriga. Through diagonal stars in the Dipper, we find the giant superstar, Murphak. Murphak is in the abundant constellation of Perseus the hero. Thus do the 7 stars of the Big Dipper signpost these constellations. Now Orion is our signpost. From the belt, 3 studs point to the great star Aldebaran. Aldebaran is the fierce eye of Taurus, constellation of the Bull. Taurus has 2 famous star clusters, the Hyades and the Pleiades. Back with Orion, Rigel and Betelgeuse point to the star Castor, together with Pollux, the heavenly twins of Gemini. Upper right in Orion, a signpost from the star Bellatrix, via Betelgeuse, leads to the yellow star Procyon. Procyon is in Canis Minor, pattern of the little dog. With Gemini our signpost, Castor and Pollux point to the stars at the head of Hydra, the sea serpent, then onwards to Alphard, Hydra's brightest star. But to find the brightest star of all, we return to Orion. A line downwards from the belt extends to Sirius, the dog star. Orion and the constellations it signposts. From the southern hemisphere, Orion is inverted, but it's the same trusty signpost. One of 88 constellations, an example of how a vivid and unmistakable star pattern helps us navigate the heavens. Anywhere on Earth, away from city lights, stargazing has endless fascination, especially for the informed observer. For a complete guide to the night sky, access our website. True astronomy began in the Middle East. From 4000 BC, on towering ziggurats, the Babylonians charted the rising and setting of the sun. They grouped stars into patterns or constellations. They understood the cycles of the sky. These ancient observers knew that the sun, the moon, and the planets moved against the background stars. The planets, as so-called wandering stars, made loops in their paths across the sky. With the sun and the moon, the planets travelled through the same band of the heavens. The Babylonians named it the zodiac. From Taurus the bull, the zodiac passes through 13 constellations. To this day, 12 of them survive in popular astrology. But these mythical figures depict real star patterns. The Chinese kept the longest continuous observations of the sky. From 4,000 years ago, they charted celestial movements with meticulous detail. They made an accurate calendar and star maps like this. The ribbon is the Milky Way. Eclipses of the sun were probably first recorded in China. Sunspots were observed by naked eye. The Chinese saw the northern lights, the aurora borealis. And they were the first to record Halley's Comet, which appears every 76 years. Chinese tomb drawings depict comets as broom stars because of their tails. The Egyptians created our calendar of 365 days. It was 3000 BC, time of the pyramids. Water was precious in this desert land, but the Egyptians knew that the first dawn rising of the dog star Sirius heralded the flooding of the Nile. Irrigation could begin and the annual harvest secured. The Egyptians, experts in heavenly cycles, believed they were controlled by gods. Supreme homage was paid to the sun god Ra. Such ideas thrived until 500 BC. Then came the Greeks. Aristarchus of Samos said the moon shone by reflected sunlight. He was right, but his idea that Earth circled the sun was ahead of its time. Instead, it was thought crystal spheres carried the stars, the sun, and other bodies around Earth. As the mistaken notion of Aristotle, it persisted for 17 centuries. Another Greek, Hipparchus, compiled the first star catalogue in the Western world, and he compared the brightness of stars. In North Africa, the Greek Eratosthenes had read of this well at Syene. At noon on Midsummer's Day, he knew the sun shone directly down the well. But north in Alexandria, also at noon on Midsummer's Day, Eratosthenes observed a column casting a shadow of 7 degrees. Using the discrepancy, Eratosthenes proved Earth was round. Simple geometry gave him a circumference of 40,000 kilometers. Eratosthenes was correct. Ptolemy was not. Ptolemy was troubled by the backward loops of planets in their motions across the sky. He explained them with epicycles, the planets dancing circles on their orbits of Earth. But such was Ptolemy's reputation, the mistake long survived the decline of Greece. Astronomy had entered the Dark Ages. In Central America, Mayan astronomers who built step pyramids had a calendar of 584 days. It was based on the cycle of the planet Venus, worshipped here as a Mayan god. With Nicolaus Copernicus came enlightenment. He resurrected the theory of planets orbiting the sun. But with the Church clinging to an Earth-centered view, the ideas of Copernicus, a Polish cleric, weren't published until 1543, after his death. Enter Tycho Brahe, the Danish astronomer, who proved in 1577 this comet was farther away than the moon. Brahe lost part of his nose in a duel and wore a golden prosthetic. It didn't hinder a brilliant career. His precise observations established a real understanding of how the planets orbit the sun. Working with Brahe, the German Johannes Kepler defined 3 laws of planetary motion. The first was that planets move around the sun in ellipses, not circles. The second was that orbital speed varies. The planet travels fastest when nearest the sun and slowest when farthest away. His third law was that planets orbit slower and slower the more distant they are from the Sun. And here, with Earth's orbit overtaking that of Mars, Kepler explained those retrograde loops. Pisa, where the great Italian mathematician and astronomer first worked, Galileo Galilei. In 1608, he turned the telescope, a Dutch invention weaker than modern binoculars, to the sky. He found moons around Jupiter and craters on our moon. Galileo saw the phases of Venus and angered the Church with his sun-centered views. In the late 17th century, the English genius Isaac Newton split sunlight into the colors of the rainbow, a spectrum. He developed the reflecting telescope, using mirrors rather than lenses to collect and focus light. And Newton worked out gravity, a force of attraction between all bodies. It explained Kepler's laws, and modern astronomy was born. In 1781, William Herschel discovered the planet Uranus. And through a telescope he built in England, Herschel mapped the Milky Way. He deduced it was the sideways view of a galactic disk. But not until the mid-19th century did the aristocrat Lord Rosse reveal the spiral structure of galaxies. He made this sketch of the Whirlpool galaxy from his castle in Ireland. There he had a telescope, for half a century, the world's biggest. The late 19th century saw two developments. One was spectroscopy, first demonstrated by Newton. Light from celestial objects could be analyzed to show their chemical composition. The other was photography, recording comets and mapping stars. A new century, and in 1917 this telescope, the 100-inch Hooker, opened at Mount Wilson, California. Through it, the American astronomer Edwin Hubble made a profound discovery from the spectra of galaxies. They were all rushing away from each other. The universe was expanding. And peering even deeper, in 1947, the first 5-meter telescope, the Hale, confirmed the expansion. Simultaneously, radio astronomy began, the start of observation in wavelengths other than light. With the space age came observatories in orbit. Free of atmospheric interference, they could peer in infrared, ultraviolet, and X-rays. The Hubble Space Telescope provided a similar clear eye for optical astronomy. Hubble images were stunning, and they were captured by a new breed of highly sensitive electronic detector, the CCD, or charge-coupled device. Chile, South America, a mountaintop in the Andes. 4 telescopes that can link as one to form the VLT, or Very Large Telescope, the latest in optical astronomy. Despite their ground base, these instruments rival Hubble with image quality, each 8.2-meter mirror providing enormous light grasp. The VLT collects these images via new technologies, active optics and adaptive optics. They compensate for telescope movements and our shimmering atmosphere. 21st century tools in the progress of astronomy. It's the late 21st century, and 500 kilometers above the surface of Earth, we approach a space station. Perhaps we're tourists, spending a weekend in orbit. Or maybe we're in transit to the Moon or Mars. For that's where the space station scores, as a spaceport. To launch a craft to the Moon or the planets needs an escape velocity from Earth of 40,000 kilometers an hour. From here, it takes a fraction of that energy. Our attempts to beat gravity began with rockets, invented by the ancient Chinese. The fuse on modern rocketry was lit by the American Robert Goddard. Goddard replaced solid fuel with liquid. From Massachusetts in 1926, he launched the first liquid fuel rocket. The Germans pushed forward development in World War II. As a weapon of mass destruction, they unleashed the V-2. It was the brainchild of Wernher von Braun, captured with fellow scientists and shipped to America. There, at White Sands in New Mexico, working with the military, von Braun galvanized American rocketry and reached to the edge of space. But the Soviet Union got there first. In 1957, they launched Sputnik 1. The first artificial satellite was in orbit. Its mastermind was Sergei Korolev. He was moving fast, developing a rocket powerful enough to carry a man into space. That man was Yuri Gagarin. On April the 12th, 1961, Gagarin blasted into history. He made one orbit of Earth and returned a hero. The Soviets were on a roll. In 1963, Valentina Tereshkova became the first woman in space. Next, 2 men, then 3 were in orbit together. And in 1965, the first spacewalk was by a Russian. Following a series of unmanned flops, Alan Shepard was the first American in space. But his mission, a month after Gagarin's, was a modest suborbital hop. Nevertheless, with a safe splashdown, American pride was restored and the stakes were up. President Kennedy declared the thrilling objective.
Before this decade is out, of landing a man on the moon and returning him safely to the Earth.
With this astronaut, the race was on. Atop a Redstone rocket and 10 months after Gagarin, America had its first man in orbit. John Glenn. Concerned, though, as a light warned of a loose heat shield, Glenn had a rocky ride. But he made it. And America was in the space race. 2-man missions began in 1965 with the more powerful Titan rocket. Including the first American spacewalk, this was the Gemini project. 10 flights that tested rendezvous and docking procedures. With the moon the objective, invaluable experience. Gemini 8 in a spin, through a misfiring thruster. But luck held and the craft survived. In 1966, the Gemini project successfully concluded. These astronauts had no such luck. In a launch pad fire, they died in their capsule. It was a tragic start to Project Apollo, but after lengthy modifications, missions resumed. Separating from the upper stages of its rocket, Apollo 8 became the first craft to break free from Earth and slot into an orbit of the moon. It was Christmas 1968. As the triumphant crew returned, everything was now tested for a landing, except the lander, and that was tried in orbit by Apollos 9 and 10. Neil Armstrong, Michael Collins and Buzz Aldrin. The crew of Apollo 11, thrust by von Braun's Baby, a Saturn V rocket, towards the moon. 3 days later, the lander left lunar orbit for the craters below. While Collins orbited in the command module, Armstrong and Aldrin made a perfect landing. They'd reached the magnificent desolation of the moon.
It's one small step for man, one giant leap for mankind.
It was July 1969. Blasting off for the command module, Armstrong and Aldrin rejoined Collins and headed home. With 5.5 months to spare, they'd achieved one president's deadline and had the thanks of another. 4 months later, Apollo 12 was on the moon, a pinpoint landing next to this unmanned Surveyor. But next up, Apollo 13 had problems. An explosion crippled the service module. Everything except basic life support was switched off. Mission Control devised ways of keeping the crew alive. And by using the lander module as a life raft, they made it back, but minus a moon landing. Later Apollo missions were less about flags and footprints, more about signs. There was exploration by Lunar Rover and the collection of over 1/3 of a ton of geological samples. Apollo 17 left the moon in 1972. Since then, no one's been back. Instead, America launched Space Shuttle. As a reusable vehicle, the aim was to cut ferrying costs into low Earth orbit. The Soviets stuck with expendable and simple rocketry. They built orbiting space stations, like this one, Salyut. Back in the 19th century, they were the dream of the Russian Konstantin Tsiolkovsky. He'd have loved the Soviet station Mir, begun in the mid-80s and the largest ever built. Aboard Mir, crew from many nations learned to live and work together. Eventually, the Americans joined in, with shuttle missions to Mir. Now we have the International Space Station, but it's much delayed and over budget. This could be the future. An aerospace plane that slashes all previous costs. Its trick is air-breathing engines. They suck oxygen from the atmosphere to burn hydrogen fuel. That saves carrying oxygen and an enormous amount of weight. Only approaching orbit do conventional rockets kick in. From airport to orbit in 10 minutes. Compared to shuttle or a Russian rocket, a budget ride on a lightweight ferry. The station could be an interchange for onward flights to the moon, just a couple of days away. Bulk transporters would ply from the space station with supplies too expensive if lifted directly from Earth. For the moon is now colonized. It's the second half of the 21st century. From lunar cities, we're mining the riches of this world next door. Again, from our orbiting spaceport, an express trip to Mars. Designs already exist for nuclear-powered rockets that will cut the voyage from 9 months to 6 weeks. The red planet will be our home from home, but it'll be life in a bubble, self-sustaining biospheres shielded from a hostile exterior. Much farther in the future, in craft we can only imagine, we may head for the stars. But to leave behind Earth, the moon, the planets and the sun, and traveling at 1/10 the speed of light, it would still take 40 years to reach the nearest star. So how long to a star with a planet like our own? Maybe this is a more immediate prospect for an escape from Earth. A tower rising 36,000 kilometers from the equator. The idea of space guru Arthur C. Clarke. The tower is one of 4 elevators to orbit, the spokes of a gigantic wheel of which Earth is the hub. Clarke's wheel is both an orbital city and a springboard to space. Planet Earth is a global village. We're in touch as never before. We observe our world from space. We monitor countryside and city. And we communicate with anywhere on Earth. Chatter and data, a network linked from orbit. From satellite. Dishes catch radio and TV. We watch images from across the world and from worlds beyond, like Mars. Kids' cartoons and global news. Telecommunication bathes the planet. Via satellite, we can track a taxi cab or a car on a freeway. And that driver can pinpoint direction, distance and position. All thanks to a web of global positioning satellites. For shipping, they're a boon. More reliable than navigating by the heavens. Strictly speaking, the Moon is our only satellite. These are artificial satellites, in this case so-called remote sensors. They monitor the resources of Earth. In farming, they detect gluts and shortages. Crop cycles are schematically mapped. In spring, red shows young growth, the rest bare soil. Midsummer, and the red is burgeoning fields of cereal. Autumn and green depicts harvested crops. Satellites spot the need to irrigate. In 2 images over 2 years, the left is dry and poor crops, the right water and plenty. Satellite imagery is a vivid overview. It makes for good harvests and effective distribution. And satellites aid pest control, like locusts that can strip crops in minutes. In these images of equatorial Africa, yellow reveals damp areas where locusts lay eggs. By targeting such breeding grounds, pesticide cuts crop damage. From satellite, cloud tracks reveal wind direction, the cycles of hot air rising and cold air falling that drive our weather. If heavy cloud is on the way, when will it rain tomorrow? Weather satellites provide hourly time-lapse. For meteorologists, an evolving pattern on which to base their forecasts. Accurate predictions are important for bad weather. Snowplows must be ready, runways cleared, plains de-iced. For vessels in coastal waters, will calm become rough? And for deep-sea fishermen, will rough become storm? Thunderstorms are easily spotted from orbit. With yellow and orange as indicators, a map of lightning flashes is invaluable in forecasting. The most intense storms spawn tornadoes. They funnel downwards from thunderclouds, whirling at vast speed. The narrow track of a tornado wreaks havoc. Less ferocious but much bigger are tropical storms. Raging in from the Atlantic, they're known as hurricanes. Satellites show where they'll hit and where damage will be, not least coastal flooding. But inland flooding causes more devastation. Torrential rain swells rivers. And because lots of us live in the floodplains of rivers, flooding can be catastrophic. A satellite image of a big river, and now flooding its plain. Another river as it should be, and here in full flood. By imaging the extent of floodplains, satellites help planners combat one of the greatest natural calamities on Earth. Satellites keep an eye on volcanoes. Not an eruption goes unrecorded. Vigilance that builds clues about future eruptions. And contour mapping that shows places at risk from ash and lethal flows. A volcanic peak from satellite. Then, with eruption points as hotspots, a heat image. Satellites detect volcanic emissions. Particles from a major eruption are tracked through the stratosphere. They can cool our climate by a degree or two. A man-made disaster as a tanker burns. An oil slick threatens coast and wildlife. It's observed from orbit and the slick precisely tracked. First, it's a snake. Then it breaks up. Satellites warn where oil will come ashore. Forest fires, often maliciously set, threaten people and property. From space, the fires are clear. So is the dying down, and so is the damage. In the United States, West Coast fires send smoke as far as the Great Lakes. A satellite studies how forest fires pollute the global atmosphere. Red shows increased levels of carbon monoxide. And there's concern at the effect of traffic pollutants, not just at street level, but globally. The same goes for factory chimneys. Satellites are watching. Our atmosphere and cloud cover are slowly changing. That seems to affect the way sunlight is absorbed, reflected and re-radiated. And that means climate change. In parts of Africa, it's getting drier. Satellite images show Lake Chad drying out. Strip by strip, over many years, satellites have scanned the planet. They've built a picture of climate change, and in the stratosphere, a depleted ozone layer. The layer protects us from ultraviolet rays, and it's developed a hole over Antarctica. Tropical rainforests are the lungs of the planet, absorbing gases like carbon dioxide. But tree felling is shrinking those lungs. Great tracts of forest are being cleared for development. Satellites record the burning. They show how quickly forest becomes farm and factory. Each minute, 1.5 hectares is lost. And when tree roots go, especially on slopes, topsoil and fertility follow. Climate change is raising sea levels, and with oceans stormier, coastal communities are threatened. Satellites measure sea levels with impressive accuracy, to within 4 centimeters. It's important because wave height reveals temperature. Warm water rides higher than cold. And satellites unveil the seafloor. For oceans aren't flat. They have contours that mimic the profile beneath. Measure the surface, and you see the floor. On average, oceans are 4 kilometers deep, and they store heat. In the top 2 meters alone, there's more heat than in the whole atmosphere. From satellite, a temperature map of the Pacific. Warm water in red is blown well away from South America, but periodically, easterly trade winds slacken. That's the time of El Niño. A huge finger of warm water trails west across the Pacific. The result is storms and floods in some regions, severe drought in others. In Australia, it means crop failure. With climate change, a concern is that melting ice will raise sea levels. Pack ice is no worry, it's already floating. So satellites monitor land ice in Antarctica and Greenland. Ice sheet thickness is logged, and so are icebergs that break away. Melting Greenland ice could reduce sea salinity and disrupt currents, and badly cool northern Europe. Satellites will see, whether in red and blue for climate research, in green and blue for taking ocean temperatures, in green and white for studies of snow and ice, or in red and yellow for scanning vegetation. The International Space Station, nightmare or dream come true? As the largest structure ever assembled in Earth orbit, hopes were high for this toehold in the sky. Built by astronauts and cosmonauts, a human colony in the hostility of space. The station was to be a springboard to the Moon and Mars, but since construction began in 1998, progress has been slow. Worst problem has been ferrying crews and materials from Earth. Shuttle was to do most of the work, the first reusable space vehicle. Blasting off like a rocket, 2 boosters gave extra thrust and were jettisoned after a couple of minutes. Within 9 minutes, Space Shuttle was in orbit. From its payload bay, Shuttle launched probes to the planets and positioned satellites. Crew retrieved and serviced satellites, the payload bay doubling as repair shop. And with an orbit of Earth every 90 minutes, daylight became darkness 16 times a day. In orbit, Shuttle traveled at 27,000 kilometers an hour, perfect for a satellite launch. Mission accomplished, shuttle slowed for the heat of re-entry caused by Earth's atmosphere. The craft was now an airplane. And a glider at that, for its descent was entirely unpowered. By 1986, 12 years before the International Space Station, the 25th shuttle crew headed for liftoff. The craft was Challenger, and this was its fatal flaw, a leak from the right-hand booster. 76 seconds into ascent, the crew perished as Challenger exploded. Shuttle was grounded. In the meantime, the Russians launched this craft, Mir, a space station that remained in orbit for 14 years. Mir was serviced by Soyuz, Russia's trusty space taxi. Crew were carried aloft in threes. Mir was continually manned. Section by section it grew. By 1995, with shuttle flying again, the American orbiter docked with Mir. There were 9 such rendezvous, and much to celebrate. International cooperation had begun. (1998), and the Russians launched Zarya, first module of the International Space Station. Less than a month later, shuttle delivered a second module. ISS, the International Space Station, was bolted together and born. 2 further shuttle flights ferried tools and equipment, but time was slipping. In July 2000, 26 months late, the Russians delivered Zvezda to orbit. Zvezda was the heart of ISS, the control and living module that would allow the station to be permanently manned. Better late than never, from Kazakhstan, the first crew blasted off. 2 Russians and the commander of ISS, an American. ISS had its first crew on November 2nd, 2000. On Earth, what goes up must come down. We are all subject to the force of gravity. It makes us feel weight. But on ISS, the crew is weightless. Although gravity still tugs, they don't feel it because they're in free fall. Crew and station are all falling to Earth. But since they're moving sideways so fast in relation to Earth, they never reach it, because Earth is always curving away. The blue boxes store American food, the red Russian. For ISS is truly cross-cultural. Indeed, parts of the interior resemble Mir. This is Zvezda, the hub of ISS where the crew lives. Food, drink, everything floats in weightless microgravity. A bubble of fruit juice. The fact is, drinks don't pour in space. Toss a candy, and it travels dead straight. Sleeping is equally odd, whether tethered in a floating bag or strapped to the superstructure. Either way, it can be difficult. Crew report nightmares, motion sickness, and snoring. On shuttle, astronauts are woken by mission control. ISS has alarms. With no flowing water, a hair wash means dry shampoo. And with no showers, washing is with towels soaked in cleaning agent. Brush your teeth, and the paste must be swallowed or wiped away. Life can be awkward and noisy. Crew complain of mechanical reverberation. Here they fix an air conditioning unit. And there's the chore of keeping fit. Braced on machines, crew must exercise. It reduces muscle wastage and loss of bone mass. But in microgravity, sorting camera equipment is easy. Taking photographs or simply looking are great joys. The coast of Chile. A deep blue lake in Kurdistan. The Dakar Peninsula in Senegal. Suiting up for an EVA, extravehicular activity, a spacewalk. Just putting on the suit takes 45 minutes. It's insulated and pressurized against the vacuum of space. Into the airlock to breathe pure oxygen for an hour, the pre-breathe. This purges nitrogen from the blood, together with a slow lowering of pressure, a guard against the bends. Another precaution, safety lines are clipped to ISS to stop crew drifting away if they lose their handholds. Astronauts usually work in pairs. Before the mission, they rehearse jobs together, for time is precious on an EVA. ISS should be growing module by module, but it's been dogged by delays. First, the Russians fell behind through money problems. Then, with a growth rate like this requiring 5 or 6 shuttle trips a year, the Americans hit trouble. In January 2003, the shuttlecraft Columbia blasted off on a routine mission. As it did so, a piece of debris hit Columbia's wing. No one realized the significance until 16 days later when Columbia re-entered the atmosphere. The damaged wing caused the craft to break up. The crew of 7 died. With all shuttles now grounded, the implications for ISS were serious. Crews could no longer be supplied or relieved by shuttle, and the building program was on hold. Once again, it was Russia to the rescue. 3 months after the tragedy, a reliable old Soyuz delivered fresh crew and supplies. Outside ISS, it was reassuring to see Soyuz safely docked. 40-year-old technology that worked. At one time, this craft was planned as an emergency return vehicle, the X-38, a permanent lifeboat. Re-entry friction would slow its descent, then parachute. Alas, funding was cancelled, besides which, shuttle would have had to lift the craft to ISS in the first place. All this leaves in doubt the future of the station. With shuttle out of service for safety fixes, the Russians maintain a presence, and they have the only means of reaching ISS. With shuttle resumed, all missions will be devoted to completing construction. Hopefully by 2010. Blue Earth is just right. 2/3 of the surface is water. We have a stable orbit, and the sun is neither too near nor too far. Since it arose, life has teemed in our oceans, an incubator of evolution. Life grew wings and conquered the air. On land, great mammals evolved. Reptiles, plant life, and insects filled every niche. Deserts succumbed to the march of life, and it thrived in polar wastes. But so far, and the hunt is on, we've only found life on Earth. Yet life comes from the stars. From supernovae, the explosive deaths of gigantic stars. They spew entrails through space, glowing debris rich in heavy elements like carbon and iron. These elements, vital to all living cells, enrich clouds of gas and dust in star-forming regions like this. 5 billion years ago, such a cloud collapsed under its own gravity. At the center, our sun fired up. From the swirling disk surrounding, thick rings of material formed, the whole system impregnated with those building blocks of life, inherited from supernovae. Formed of an inner ring 4.5 billion years ago, our proto-Earth emerged. But this was no place for life, a semi-molten rock bombarded for hundreds of millions of years. Slowly, as impact subsided, the solar system took shape. But of the 9 planets seeded from ancient supernovae, only one would blossom. And not until Earth cooled, some 3.8 billion years ago, did those seeds stand a chance. Volcanic eruptions constantly resurfaced the planet, low-density rock forming on land, high density on the seafloor. For by now there were oceans, condensed from the water vapor of eruptions and carried to Earth by comets. Perhaps they also brought life. Gases from the interior composed the early atmosphere, largely nitrogen and carbon dioxide. Lightning, just possibly, was a catalyst. But where on this cloudy and bubbling planet would the spark of life have struck? Volcanic hot springs could be the place, rich in chemicals essential for life. Fossils suggest single-cell organisms began here 3.8 billion years ago. They were called prokaryotes. Deep in the oceans, more evidence. Around smokers, prokaryotes clustered, but they were tied there. Only when they photosynthesized using sunlight did they go green and colonize the world. Photosynthesis changed the atmosphere. These are stromatolites, formed in shallow water about 3.4 billion years ago by photosynthesizing microbes. Photosynthesis released oxygen. The atmosphere became oxygen-rich. A protective ozone layer developed, and oceans had the first oxygen-breathing cells. They became multicellular. Sexual reproduction began. Life exploded and diversified. Every 12 million years, the number of species doubled. External skeletons appeared some 500 million years ago. 30 million years later, fish had the first backbones. Then the Great Leap, as life emerged from the sea. Simple vegetation took hold, greening the land with the likes of ferns. Insects evolved and reptiles, ruling the world as dinosaurs. Then came birds and flowering plants. And mammals, monkeys and man. Such a blooming of life is thanks to our position in the solar system, third rock from the sun. We orbit in the middle of the habitable zone, here in green. Mars and Venus are at the edges. Life may have tried on Venus, but cloud conceals a pressure cooker where nothing could survive. This hellish world is rather too close to the sun. Mars is at the other extreme, too far from the sun, slightly beyond the habitable zone. The red planet is cold, dusty and dry. Yet little over a century ago, Mars was thought by some astronomers to have canals. They'd been dug by intelligent beings. Today we know better. Maybe water flowed, but not in canals. This valley was probably carved by water. And here, signs of flash floods. For long ago, Mars was probably warmer and wetter. Surely this can only be a dried-up river system. Today, however, this is the reality, a barren waste. Had there been life, it would be microbial and less easily detected than the icy remnants of water at the poles. This is Europa, a moon slightly smaller than our own, orbiting Jupiter. Europa may nurture life. But not on the surface. Sheet ice covers the entire moon. Fractured and faulted, it resembles frozen seas on Earth. And as on Earth, an ocean may lie beneath. These markings hint at disruption from below. In the depths, volcanic vents may spout. Around them, feeding on their chemical nutrients, simple life could thrive, bacteria-like organisms deep in a sunless sea. Beyond Jupiter, it's just too cold for life. Indeed, apart from the profusion of our own planet, there's still no evidence for life, past or present, anywhere else in the solar system. So we must look to the stars, to different suns with different planets. We can't see the planets, but we can detect their presence. The distorted disk around this star is caused by a huge planet. And this stellar ring may signify a planetary system like our own. When the glare of the star Beta Pictoris is masked, a disk of gas and dust is revealed. But it's slightly warped, possibly by the orbit of a large planet and its gravitational tug on the disk. Astronomers are beginning to think planet formation is a natural byproduct of star formation. Here in the Orion Nebula, stars are forming from clouds of gas and dust, as did our own sun and the planets. This is a young star in a cocoon of dust. Such cocoons are the stuff of planets. Edge-on, cocoons are flattened disks. Around their star, planets in the making. A star with a planet has a common center of mass, the green dot. The two bodies revolve around that point. Although the star exerts a far greater pull on the planet, as it orbits, causes the star to shift. That little wobble is how scientists find a planet, even though they can't see it. They can work out the orbit and mass of the planet by comparing the shift in the star's spectrum, below, with the reference, above. The method has detected well over 100 so-called extrasolar planets. This one, resembling Jupiter, orbits 51 Pegasi. But there's no hope of life on the planet. It's too hot and much too close to its sun-like parent. The wobble method discovers only big planets. Smaller ones, like Earth, haven't the mass to cause detectable shifts in their stars. But this instrument should discern such planets. To be launched into Earth orbit, it's the Terrestrial Planet Finder. Highly sensitive and with revolutionary imaging, the instrument will scan the habitable zones around stars. There, on benign little worlds, life may flourish.